What is up, Brad fans? How you doing? Hopefully really, really well. And let me just say, I'm excited to bring you every episode. But I'm really excited to bring you this episode. Why? Because we are once again talking about that subject that will get you shadow banned from Twitter and Instagram, allegedly. That's right. Ivermectin. Why? Because there's a big new trial that's just been released, probably about a month ago. You may have heard. It does nothing for COVID, just as we suspected. So this was one of those big trials that we had teased in earlier episodes about ivermectin, saying, wait for the data. Let's wait for a really good controlled trial with a big sample size, placebo group, and let's see what happens. Now we know what happens. It doesn't work for COVID. Not only does it not work, it looks like the trend in the effect of ivermectin on COVID was negative. So this just means that if you saw a positive trend, for example, but your data wasn't significant, you might say, oh, well, let's just increase the sample size and then we'll see an effect. Problems with that logic aside, this was actually the opposite. So it looked like if you increased the sample size and kept going, the people that took ivermectin would actually do worse. So it really doesn't seem to work. I think we can kind of put the nail in the coffin on this one. And to all those people that are touting all the ills of the pharmaceutical industry, scandals, greed, all of that stuff, we're not even going to go into the logic of, well, just because that's true, there are scandals and they are greedy at times, we should get rid of them all, or ivermectin works, or they're keeping it from us, all of that stuff. Talk about, babies in bathwater and cutting off your nose to spite your face. Like it doesn't make sense, but you still have to look at the data. Carefully controlled trials, double-blind placebo trials, which we now have that say this drug does nothing for COVID. But you know what? We're not even going to talk about that. We're not going to talk about all the ways in which the pro-ivermectin COVID people are wrong. Because if you listened to this story since the beginning, you probably heard a lot of these podcasts, pundits, whatever, pro-ivermectin for COVID people tell you what an amazing wonder drug ivermectin is, and how safe it is for humans, and how it's been used in humans for years, how there was a Nobel Prize that was won because of the discovery of ivermectin. And you know what? That's all true. All of those things are true. And that's what we're going to talk about today, because all of those things are true, and yet the reputation of ivermectin has kind of been tarnished by these people that keep, insisting that it works for COVID when it doesn't, and then the politicization and the media coverage and on and on and on. So let's actually sit down and talk about the true history of ivermectin. Where does it come from? How did we discover it? Did you know it was discovered on a golf course? There's a bacteria that produces the precursor to ivermectin, and it was found on a golf course in Japan. Fascinating. And the story of its discovery is actually a great story of serendipity, scientific discovery, how scientific discovery works, the scientific method, all of those things. So we are going to talk about that. We are going to talk about how it works on a molecular level. Why is it so good at killing all of these different types of parasites? Because yes, that is what it's designed to work against, is roundworm parasites. We are going to talk about resistance. What do we know about parasites developing resistance to this drug? There's actually a lot about ivermectin that we don't know, which again is an interesting story about how science works. You can spend your whole life studying ivermectin and still not understand everything about it. It's also giving us interesting insights into how the nervous system works. You'll hear about that. We will talk about why ivermectin always comes up when it comes to drug repurposing for new diseases. So what is drug repurposing? How does that work? Why is ivermectin always on the list of, hey, there's a new disease, let's throw some ivermectin at it and see if it works? And then we will talk about the sort of controversy, the media controversy, and what maybe we can do as science communicators, as scientists, to avoid a situation like this in the future. And to help us through all of this is my guest, Dr. John Gilleard. John is a great veterinarian and a great research scientist. And I consider him a great friend and a great mentor because John was one of the supervisors of my PhD thesis. So I worked in John's lab for about 5 years. We became quite close. He's a great friend and a great guy to talk to, and the perfect guy to talk to when it comes to ivermectin, because his lab has studied ivermectin from the point of view of resistance. How are parasites developing resistance to ivermectin, which, as you'll hear, is a big problem. He studied this for decades. So he knows the ins and outs of ivermectin, and it was a pleasure to have him on the show. But of course, before we get to that, as always, reach out to me, reach out to the show on Twitter, Instagram, @2bradforyou. Go to our website, 2bradforyou.wordpress.com. There you'll find the email address. You will find a voicemail box. You can leave a comment there. Please do rate, subscribe, leave comments wherever you're getting your podcast. That really helps out, boost us up in the charts, boost our visibility. So thank you to all those people who have done it. If you haven't done it, please subscribe, rate, review, all of those things. If you have done it, do it again. Why not? And with that, please enjoy my chat with Dr. John Gilleard about the true history of ivermectin. John, thanks so much for taking time out of your morning to do this for me.
It's a pleasure. It's good to be here on whatever platform we're on.
Yeah, Squadcast. I don't get any money for saying it, but I'll support them
anyway.
anyway.
There you go.
So we work together, as people will know from the introduction, and you were one of the first people to actually ever come on my podcast way back, probably 3-4 years ago now.
Yeah.
Things have changed. We've both grown a little older, a little wiser, I hope.
Yeah. Well, certainly older. Yeah. I remember that. I remember that one well because it was in the house, actually, wasn't it?
Yeah.
And you came over to the house and, you could hear the toilet flushing and things like that, which added atmosphere.
So we shouldn't have that problem now, but, my little one might be banging on the door at some point, so you may hear that. But other than that, we should be okay. We went back and forth on what we could talk about on this. We wanted to catch up. It's been a while since we've seen each other, but what do we make a podcast about? And ivermectin came up.
Yeah.
Because something well, and maybe I'll start by telling you this story, but I got called a shill for Big Pharma on Twitter. Can you believe it?
Really?
Because I wrote basically a paper summary for some medical news website covering one of these, trials that said ivermectin didn't do anything. Yeah, and it's not. This wasn't like a piece of, this isn't one of those works where I'm like, I've pitched the idea and I wanted to write about ivermectin. It's like, no, someone paid me to just summarize this paper. So I didn't promote it on Twitter. I wasn't putting it up on my website or anything. So this guy from Alberta, naturally, found this somehow and then did the effort to find me just to shout at me on Twitter, say that I'm a piece of garbage and I should stay in Germany and it's a good thing that I left Alberta.
Sounds typical of the type, yeah.
So that actually got me started on going down the ivermectin. Does it work for COVID and everything like that? And we'll get to that. But what we can do here, because I have you, who's veterinarian, has worked with ivermectin, has studied it in different, projects in the lab and stuff, we can actually discuss the true history of ivermectin.
Yes.
We can cut through all of this crap and get down to the truth of the fact. So why don't you take it away with, you can give us a little bit of your credentials, like your bona fides in terms of understanding this stuff, so that the guys on Twitter don't at you with a bunch of.
I don't think that matters. I don't think that has any effect at all. But no, I mean, you're right. I mean, it's one of the things we've studied. I mean, I study it more from a drug resistance point of view, right? So, in animal parasites primarily. So over the years, we're studying how parasites, and particularly worm parasites, become resistant to this drug, which we'll talk about more, obviously. More from the parasite point of view and the genetics of the parasite and improving diagnostics and those kind of things, rather than the pharmaceutical end of it. So that's kind of what we do in the lab and my research program, and we might touch on some of that in amongst it all. But so that's, if you like, my credentials of kind of worked on it a lot. And it's one of those drugs which, if you work in parasitology, it's difficult to avoid, really, because it's so important.
So then let's maybe like touch on that, because like when it was discovered, and I don't know the exact year, maybe you know that, but it was really like kind of one of these sort of wonder drugs in terms of
Yeah.
treating parasites, almost like penicillin was.
Absolutely, it is. It has been, called a wonder drug, and actually, one of the things that is a bit of a shame about the current, controversies and why it's in the news, which I'm sure we'll get to, is it's almost being kind of tarnished in a way in terms of the public perception of it, right? And so, in terms of does it work, does it not, and all this kind of stuff. But it is actually, for parasitic diseases, probably arguably the single most important tool that we've had. Certainly one of two or three, maybe, of controlling parasites both in animals and humans for, best part of 20 or 30 years. So it's a hugely important drug. And as you say, it was, and actually, I'm trying to remember the year. Oh my God, I've gone blank. 2015, 2015 Nobel Prize for Medicine and Physiology was for the discovery of ivermectin. Right. So it's a big deal. So it all stems back to kind of the 1970s, actually. And it is a really interesting story of drug discovery and serendipity and all those things. So there was a guy called Satoshi Omura who is in Japan, and he was a kind of microbial chemist, I guess you'd describe him as. And what his thing was, he would take bacteria from the natural environment and look for bioactive molecules which might have some medical value or agricultural value even. So he was particularly interested in a group of bacteria called Streptomyces, which has a strong history actually of in drug discovery, because there's probably the second broad spectrum antibiotic, I think, streptomycin, which is actually a product of Streptomyces. So in sort of antimicrobials, it had a history of yielding, or that group of bacteria had a history of yielding drugs. So he was, basically looking at lots of natural isolates of Streptomyces and categorizing them and looking for bioactivity. And then he developed a collaboration with a scientist called Bill Campbell at the Merck drug company in the US, who was a parasitologist. And so he would screen these compounds or these organisms and the things they produced for activity against parasites. And so that's kind of the dynamic. And there's one set of these kind of Streptomyces cultures. So what he would do, he'd grow them, look for some kind of bioactivity, and to be honest, I can't remember the first screen what that would be, and then selected them from that and shipped them off to Merck, right? And so these, there's one set of 50 or something that got sent to Merck. One of them was isolated from a Japanese golf course. So just literally go around in different places in the environment, culturing bacteria, finding Streptomyces and, et cetera, et cetera. And so this one, which was from a golf course in Japan, when Bill Campbell was screening for it, and he had this screen of a parasite with a terrible name, Helicomysoides polygyrus, which is a mouse parasite. So it's a mouse model. And they would you look at the activity of these culture supernatants, essentially, when given to mice, how they killed the parasite. This one worked incredibly well. I think the first test they did also killed the mouse as well, but that was, I think that was something else in the culture. But anyway, it basically, that's where it started. And then Bill Campbell and his group then isolated and identified the compounds, which were these ivermectins. And so there was a mixture, I think, of 4 different ivermectin compounds, which are these things called macrocyclic lactones. And it's quite a big organic molecule in the sense of, for a pharmaceutical. So I can't remember how many. It's got like 18 of these carbon rings. And so it's quite complex. So you can't really synthesize it. So the way it's produced is still from the bacteria, right? Which culture, and then they modify it chemically afterwards. And
really?
So ivermectin's still is a chemical derivative of Ivermectin, which is the natural product, and there's a chemical modification which I cannot remember exactly what that is off the top of my head, but it's just like one hydroxyl group or something, and basically that is ivermectin, and that's what they used. So that was the if you like the basic discovery. And so what that
The origin story.
yeah, and then what they did. I mean, I don't. Just interrupt me if you want to take me off in a different direction. But
Well, no, I will interrupt you here because I think it just to like sort of clarify this, because I think it's an interesting point, is that you take these bacteria and they have these natural, like they've evolved these chemicals to, or molecules to fight off different things, and then you just say, and this is
yeah,
actually how like a
yeah,
lot of drug discovery done. I think this is an important point for the audience and
yeah,
stuff, is that like this is where a lot of our
absolutely,
penicillin was the same story, right? But it came
yeah,
from
exactly, yeah.
a mold or a fungus or something. So you have all these. So I'm surprised to hear that like they haven't now figured out a way to make it synthetically in the lab, and you still, to get ivermectin, you still have to grow a bunch of bacteria and get this stuff out.
Yeah, it's a complex molecule, right? And I think I mean, and actually, subsequent work they did was interesting as well, because they did a combination of chemical modifications and also mutagenesis experiments on the bacteria. Basically, you screen for mutants of the bacteria, which produce slightly different versions of the. So they've mapped the whole biosynthetic pathway, and there's certain mutations which change those enzymes in that pathway, which will give a slightly different product. So there's things like doramectin, selamectin, and a whole number of others, which all have slightly different pharmacological properties in terms of potency, toxicity issues, and things like this. So there's now a whole family of these things, and some of it's done by chemistry on the original kind of ivermectin molecule, and some of it's done by mutagenizing the organism. So it's kind of fascinating, that side of it. So there's a lot of science subsequent to the original discovery of the original compound. So that, yeah, so it is fascinating. And then the other kind of sidebar, where the serendipity comes in, is they've tried to re-isolate this organism from the environment over the years. I should say this was done back in the 70s, right? So since then, they've never re-isolated that strain of Streptomyces called Streptomyces ivermectinus, and they've never actually.
So they've never found it again?
Yeah. Correct. Yeah, never re-isolated. They have isolated another one which produces a slightly different family called milbemycins, and so that's been isolated, which is a different Streptomyces. But that original species of Streptomyces, as far as I'm aware, and again I'm going off what I've read, but I'm pretty sure it's true. They've never re-isolated the
wow
original.
He got it from that. He got it from that one golf course that one time.
Yeah.
And we got this wonder drug from it, and that lineage has been in the lab for,
It's amazing, isn't it? Yeah, and so it just shows you how luck plays a role in these things, big time, right? And how many things are out there to be discovered, which just by luck we haven't discovered, right? And actually, going to your point about these natural products as drugs, that was big in the 70s, 80s, maybe the 90s. And then there was a big trend away from it in pharma, where, chemical synthesis and these big combinatorial libraries that they produce with small molecules, and they do it all chemically. So it's synthetic chemicals, which they screen. And that became the kind of, and still is to some degree, the way it's done. But now there's a bit of a resurgence, or quite a bit of a resurgence, of these natural compound screenings again. So there's almost two ways you can discover drugs, if you like, from the chemical point of view. Is you synthesize things, and there's lots of high throughput ways of producing lots of chemical variants to do that. But then there's this screen of natural products, and that things go through fashions, right? So the natural looking for things from the environment fell out of fashion, but has come back again. So,
well, I imagine that there's a cost motivation in there too. Like, I don't know what's cheaper, like sending people out on these missions to get these dirt samples that may or may not do anything, or all the lab equipment that it takes to synthesize all these chemicals. I mean,
I think the reason the chemical synthesis became so popular is because it's scalable, right? If whereas actually sending people out to find natural products and screen them, it's less scalable, right? So it's difficult to automate. It's difficult. So I think the feeling was in the drug industry that this scalability of synthesis and all the wonders of chemistry would be the answer to drug discovery. And to some degree, it's a great thing, but I think they've realised that actually it's like all things. It's not quite that simple. It doesn't always produce what you're after, and therefore going back to the natural things is a part of the mix now again. So, yeah.
Well, and like I think there was probably an enthusiasm as some of the chemical technology took off. You see this a lot. Once there's a technological advance, it's like, oh, this is how we're doing it now because this is, the wonderful new toy and it's going to bring all this great stuff and blah, blah, blah. And then you realize, well, it's not as good as it was. And let's go back to basics. But so maybe for the people that want to yell at me on Twitter about for the evils of pharma companies and stuff, these things are natural products.
Yeah.
So it fits into the whole back to nature. I only put natural things in my body kind of thing. So there you go.
Yeah, no, absolutely. Well, it's a whole nother topic, isn't it? The assumption that natural things are good and chemical things are bad, or synthetic things are bad. There's plenty of natural toxins in the environment as well, right? So this, it's an interesting view. But you're right. Some of these drugs and pharmas are, and this is a good example of one, is actually produced essentially out there in nature.
Yeah, and I know with we mentioned resistance, whether it's to the parasites or bacteria. I think that's also one of the reasons that people are going back to nature for these things is because resistance evolves so quickly to the things that we have. So we gotta find new things. We're running out of ideas, and who's a better creator at the arms race between different species and the immune system and stuff than evolution, right?
Absolutely, and it's what I mean. A complex molecule like ivermectin, it's nature produces incredibly complex chemistry, right? And so which is difficult to recreate. So even with all the chemical knowledge we have, so it's it's pretty amazing, really.
So then they now have ivermectin. You could produce it in the lab and stuff, but it was screened in a mouse model first. So I imagine its first use was for animals.
Absolutely, So I guess the next part of the story was what they did at Merck and Bill Campbell and colleagues. Basically, they basically screened as many parasites as they could, because once they realized they had this thing, it's like, well, what will it work against? And so the next part of the story, in terms of the wonder drug side of it, is the spectrum of activity was remarkable. So they screened against a number of different gastrointestinal worm parasites, and it had activity against various ones of those, not all of them, but a lot. And then filarial nematodes, which are roundworms, which are living tissues, which is a completely and they're very phylogenetically distant from some of the roundworms that we get in the gut, and they're transmitted by arthropods, and discovered they worked against those. And the first ones they were checking on those, again, were animal parasites. There's something called heartworm in dogs, which is transmitted by mosquitoes, which is a big deal in Europe and in North America in terms of pet animals. So there's a big potential market there, right? So and it had activity there. And then they screened it against arthropod ectoparasites. So things like everything from fleas to lice to mites. And it has broad spectrum activity against those. So now you've got this drug which, started off with one worm in a mouse, is it would be exaggerating to say every parasite, but a significant proportion of parasites of all different types, right? So as you say, then it was launched as an animal health product, and again, there's it's all to do with money, right? So if you think it will come onto the human side in a little while, but there's not much of a market on the human side in terms of commercially, as we'll discuss, but on the animal health side, it's a big issue. So if you look at cattle and sheep and horses, every animal you look at in a field is full of gastrointestinal roundworm parasites, and they can have effects on production and health, and so it's money, and and controlling those actually pre-ivermectin and a couple of other drugs around the same time in the 80s was very, very difficult. And this product was launched primarily for livestock parasite control. And actually it was the biggest within a few years of its launch, which was in the mid-80s or early 80s. It was the biggest single-selling animal health product of the animal health pharma bar none, right? So it was massive. And then it was repurposed for companion animals for things like heartworm and gastrointestinal parasites in dogs and cats, and it's just this huge veterinary drug and market. So that's where it started.
Right. So then let me ask this, because you say like it works on all of these different parasites that are, as you mentioned, distantly related. So what is it? Like how does ivermectin actually work to kill or slow down the parasite? That's obviously it's something that's conserved in across all of these distantly related
well, that's
species.
the interesting thing, because it isn't kind of thing. So I think, basically the drug acts directly on a number of different ion channels, right? So it's a neurotoxin, if you like, for the parasite, but it acts on quite a number of different classes of these ion channels.
And ion channels, just for people they pump things in and out of the cell.
Yeah. So if you think of neurotransmission, and you think of one nerve attaching to another and sending a signal between nerve cells, or attaching to a muscle and causing a muscle to contract by a neurological signal, happens at a synapse. And so the synapse is the end point of a nerve traveling down a nerve fiber. It triggers release of chemicals in the synapse, which is the nerve ending, if you like, which then diffuses, and then these chemicals bind to these ion channels on the next nerve and open them up and
pass
the signal along, if you want to put it that way, or at a neuromuscular junction. So these drug, or ivermectin, binds to these ion channels on the postsynaptic nerve membrane, and so what it does, it actually opens the channel. It actually opens the channel, and so therefore that kind of causes hyperpolarization of the postsynaptic membrane. And depending if that's, and then it gets into the details of what that neuron does, right? Because if it's a neuron which is an inhibitory neuron, it can cause, one effect, where if it's an excitatory neuron, it causes another effect. If it's doing muscle in this part of the worm, it's going to have a different effect. So actually the effect on the worm can be quite complex, depending on what neurological target in terms of the cell it's acting on. But essentially, it acts on these different ion channels, and there's lots of them. I mean, there's dozens of different types of ion channels that we all have, and all organisms with a nervous system have. And so it basically acts on different ion channels at different potencies. So at low dose concentrations, it acts on things called glutamate-gated chloride channels, which are specific to invertebrates. So we don't have them. So that's why on those particular,
that's why there's a safety.
Yeah. So it doesn't. But if you increase the dose, it starts to act on other ion channels, such as things like GABA ion channels, which is gamma butyric acid, which is one of these chemical signals, which we do have in our central nervous system. So if you up the dose far and further and further and further, so both on the parasite starts to have different effects at higher doses, and then on the host, be it animal or human, if you go high enough, it will start to have some kind of effect on our nervous systems, right? But that's way beyond the therapeutic, doses which are licensed, of course. But so basically it acts on these ion channels, primarily at the doses that are used therapeutically, these ones which are specific to invertebrates, which gives you, as you said, the safety of the therapeutic difference between the host and the parasite. And then, but it gets, you can edit this out or stop me as we go, but it gets more complex again, and there's different fascinating parts to it. So if you take the gastrointestinal worms, it mainly acts on these neurons which innervate an organ, if you like, the worm's throat, its pharynx, so it paralyzes the feeding organ of the worm, right? So the worm can't feed. At higher doses, it will paralyze effect on the nerves, which affect or innervate the body wall muscle of the worm. So it causes a paralysis of the worm. So it does two things to the worms, and depending on the species of the worm and the dose, which of those is. But generally speaking, it's the feeding effect we think is the most important effect, and that's on the gastrointestinal worms. The interesting story on the filarial parasites, which are these tissue-dwelling parasites, is it acts on ion channels in the same way, but its effect on the worm is completely different. So these tissue-dwelling parasites, there's a number of different species. We can kind of talk more about them if we get to it. But basically, what they discovered was if you take the stages, the progeny of these parasites, these baby worms, if you like, the larvae. The drug acts very effectively in vivo on them. So if you treat a person with ivermectin, it will clear these larvae from the person. Works really powerfully.
Right.
If you put those larvae in a test tube and throw ivermectin on it in a lab, it does nothing to them. So they're perfectly happy swimming around in it. So this started kind of investigation. It turns out, to cut a long story short, is, the current hypothesis, and there's good evidence for it now, that ivermectin actually affects nerves which affect the release of molecules which the worm secretes into the host. So worms within the host pump stuff out, right? It stops those things being pumped out by the worm. And what those things that are pumped out do is they damp down the immune system. You can think about it, the drug is decloaking the parasite to the immune system.
And then the body can just take care of it.
Yeah, exactly. So without a good immune system, the drug doesn't work. So on the gastrointestinal parasites, it's paralyzing them, stopping them feeding. On the tissue-dwelling parasites, it's actually stopping them doing things to evade the immune system. And so, although it's working on ion channels, right, affecting the nerve system of the worm, but depending on what those nerves are doing and what their functions are, it has different implications for the parasite. So as you go deeper and deeper into it, it gets more and more complex, right? But it's fascinating.
It's. I mean, this is like a good example of, the complexity of life, but also the simplicity of it.
Yeah.
Because we have these ion channels that, basic thing that's found in all these different forms of life, but they do so many different things.
Yeah.
Like they're in charge of all of these different things. And then you have this molecule that, can bind to this one, not this one, this one, not this one. And it just creates this, like, it's really kind of mind boggling. And it kind of makes you think how, you said serendipity, right? Like in terms of governing this thing, but it kind of makes it feel like so random. Like, do we even really know what we're doing? We find this molecule and and we know it works. And then now we got to try and figure out how it works. Yeah. And once we start looking at how it's actually doing what we're witnessing it doing, it's like a whole nother mystery and just unraveling of this thing. It makes you realize, like, well, we'll never really know everything.
I mean,
like, it's a daunting.
Yeah, it is. And I think, we understand a lot about it now, but there's a lot more to understand. And you can go back again, philosophers about research and things, right? Is people, I think, who are not in science wonder, well, how can you keep researching? Like if you say you work on a drug like ivermectin, and we work on other things as well, but you could have a whole career just working on that, and you would never run out of things to discover about it because it's complex, right? And actually useful things come out of that research, understanding things at a deeper level, right? Because so I think
well, the biology of ion channels, right?
Exactly,
and this other stuff,
and things like ivermectin and many other things which act on ion channels are actually used in fundamental research as an experimental tool, right? So has a whole other life in another way in neurobiology, right, and things like that. So it's it's endless. It's really. I mean, I knew it was the wonder drug, and I know at one point you had absorbed this knowledge by being in your lab that it worked on ion channels, but I must say I didn't realize it went that deep. It's incredible. In terms of resistance then, do you see resistance evolving in all of the species that ivermectin works against sort of at the same rate, or are some becoming more resistant than others? And what do we know about, the mechanism of resistance? Because it's always this back and forth, right? Like the evolutionary arms race. Yeah. And actually, not to worry you, but we understand less about the resistance than we do about the mode of actions, actually. To start it's a good question because, the short answer is it varies a lot between parasites in ways that partially we understand, in some ways we don't understand. In terms of the gastrointestinal parasites, that's where we see at the moment the biggest resistance problems in animals. So where this drug is being used, so there's a whole variety of parasites that in livestock, for example, live in the gastrointestinal tract and cause these problems I've talked about. And ivermectin started to be used very heavily, shall we put it that way. And actually on the veterinary side, in most countries, although it's changed actually in relative recent years in Europe, as always, Europe's often ahead of North America in these matters, but it actually is prescription only in some countries now. But for many years in many parts of the world, and still is, you can just buy it off the shelf, right? If you're a farmer, you can buy this stuff from a merchant, right? So
and give your animals as much as
yeah,
you want,
exactly, whenever
you want.
you want it, right? So I think that's, and as people quite naturally, because it is this wonder drug, where parasites were the bane of many livestock owners' life in terms of disease and production, it became this tool that all these problems seemingly went away. So people would use it, like, it became cheap. Once it went off patent, it became very cheap, and you get lots of generic versions of it, which essentially work. In some parts of the world may not be as good as they should be, but some of the generics are absolutely fine. So people use them, and it was heavily used, and so we've got resistance. And if you look in some parts of the world with some parasites, it basically doesn't work right anymore. Yeah, and so things like Homoncus, which is a blood feeding parasite that I work on in sheep, and all the cattle parasites, it's essentially useless in some regions, right? You go as far as that.
Wow.
And it's just because we've selected for resistance. And then, if you look at the tissue dwelling parasites, resistance is a lot less common. But the dog heartworm I talked about, it's been used, and it's complicated how it's used actually, because it's used as a monthly, in dogs with heartworm. The problem is I have to describe the whole life cycle to explain it properly, and we don't have time
That's
for
right,
that.
we got a bit of time.
Yeah, exactly. This could take days. but basically it's transmitted by mosquitoes, and the microscopic larvae. The mosquito bites the dog, it migrates through tissues, ends up in the heart, and grows to a big worm in the dog's heart, right? So the way it's prevented is by giving ivermectin monthly, and that blocks the infection by these larvae coming from the mosquitoes. It doesn't act against...
So it's like a prophylactic.
Yeah, it doesn't act against the adult worm, it just blocks these things coming in. So you have to give it regularly. And so that's been done for many years. Resistance didn't seem to be developing, but about 7 or 8 years ago, it's now been confirmed, and we don't know how widespread it is, but there's definite cases of resistance in these filarial parasites now. So it's coming there where for many years it doesn't seem to be a problem. So on that group, it's slower to develop, and we don't know why. Well, some of it is to do with the genetics of the parasites and how variable they are, and how there is, because you need genetic variation to respond to drug selection.
Right.
And so things like that. But there's lots of complexes about the biology which might affect the rate at which resistance develops, which is probably a whole nother podcast, actually, to go into the details of that. But.
So for the purposes of the COVID controversy, which we had talked about and stuff, just at the beginning, it is used in humans. So it's not like we had this discovery, we now know this stuff, we know how it works in worms, in animals. So then the idea is naturally, well, let's look at, can we get a dose that works safely in humans for human parasites? And the human parasites and the animal parasites, again, are related.
Yeah.
The gastrointestinal worms that you find in animals are similar to the ones you find in humans. The filarial ones, same thing. So it was a natural sort of leap to be like, well, we could use this in humans. But you said the commercial incentive isn't really there, because a lot of these parasites are problems in poorer countries that can't really afford to buy the drug, which I think I've talked about on the podcast before. So maybe we don't need to go so much into that. Yeah. Needless to say that there is a precedent of using it in humans. So it's not like when COVID came along and people said that it might work, that it was totally out of left field. Do you know of any other off-label uses of ivermectin for other than parasite disease?
Yeah, I think it's mainly...
I should have looked this up. That's my bad.
No. I mean, it's mainly parasite control of different types, right? So it's got a huge number of different applications, as we said, on the animal health side, and quite a number of different applications for human parasites, as you said, because it was repurposed mainly by the, kind of philanthropy of the pharmaceutical industry. And we've talked about that before, as you say, which is basically led to it being used for a whole variety of different parasites. It's been explored for repurposing for other things, everything from cancer research to as an antiviral, and has been explored for those things. but I'm not aware of it clinically being used for them.
Okay.
Outside of that, there is one actually, which I'm trying to desperately remember it. That it does. It was. I don't think it's like heavily used, but it has been clinically used a number of years ago for some neurological conditions in humans, and I think it was there's some kind of paresis syndrome that has been used, on a clinical trial basis and actually been used as a therapeutic, but it's not like widely used for anything like that. So I might be missing it myself, but I'm not aware of it being repurposed for a completely different purpose yet. Although
Right.
it's always on the list of when people talk about drug repurposing, because repurposing of drugs is a big thing these days. We should maybe explain that very briefly because,
Yeah.
drug discovery is extremely expensive. To go from what we're talking about with the ivermectin story to a product takes many, many years and it takes billions of dollars of investment. And that's one of the problems the pharmaceutical company has. And when people bash big pharma, some of the profit drive is to produce new products, right? So it's not all greed. Some of it obviously is in shareholder companies, but nevertheless, it does take a lot of investment. And a lot of that is a regulatory side, the back end of it, where you're doing safety clinical trials and, the different phases of clinical trials, 1, 2, and 3. It's hugely expensive. So if you can take a drug which has already got an application in one area and find it does something else, it's way cheaper and faster to then just do whatever trials you need for that one thing, because all the safety stuff's probably done and all that kind of stuff.
Right. All the basic fundamental stuff is already there. Yeah.
So there's a big interest in form of repurposing. So, all these drugs which are out there or things that didn't quite make it are being screened all the time for other activities. So the ivermectin story with COVID is a typical story in some ways. It just didn't hit the media, right? It's just constant. People are screening known drugs or compounds which have some activity but didn't quite make it for new applications all the time. And ivermectin is a common one, which people, because it has some antibacterial activity but has never really been taken to the next stage with that. So it has activities against all sorts of things. So one day it probably will, but it's complexity of use. I mean, on the human side, just going through the parasites again, there's these filarial tissue-dwelling nematodes, which things like cause elephantiasis. There's the river blindness, which is another filarial nematode in Africa, which is transmitted by black flies. Scabies, which is a mite infection, is becoming the treatment of choice for that. Strongyloides, which is another gastrointestinal nematode, which can be a very severe disease, and 70 million people, it's used for that. It's been trialed as a combination therapy with other gastrointestinal nematode called Trichuris. So, the list on the parasite side of new application goes on and on and on, and that's all on the human side. There is one interesting thing, which is a bit different, and that's in mosquito control and malarial control. World Health Organization have now a roadmap to try and develop ivermectin as a part of the malarial control toolkit. And the way that works is people who are treated with ivermectin, if a mosquito bites them at that point, because it has activity against all these invertebrates, it kills a mosquito, it feeds, right? So there's regimes that have been trialed where if you treat people several times during the high transmission season, at a population level, it will really reduce mosquito populations and transmission. And if you mosquitoes also have a reservoir on livestock, they feed on livestock as well. So if you treat livestock in a controlled fashion as part of a program, the idea is you can reduce mosquito populations. You wouldn't use that alone, but it's part of a toolkit. And so that's been proposed. And it also actually, it does seem to have some effect on the liver stages of Plasmodium, which is the malaria parasite. And that's not well defined as to how effective that will be clinically, but that's another part of that picture. It might also have some direct antimalarial activity. So that's kind of an emerging new application. So although it's acting on an arthropod, it's really about controlling malaria, right?
But so this is I guess my point is that like you mentioned, ivermectin's always on this list when a new disease pops
Yeah,
up or a
yeah,
new thing, especially an infectious disease, especially a parasitic disease. It's always good. People are always going to try it because it is this wonder drug.
yeah,
It's worked on
yeah,
so many things. It's like, why not just throw some
exactly.
ivermectin at it and see what happens? So it wasn't unheard of, we'll say, to try it,
Yeah,
right? But then, and this is a point I think is worth beginning this whole section on, the COVID
yeah,
controversy, because you mentioned that you can see activity on some things. So you
yeah.
can see activity of ivermectin on bacteria or the liver stages of malaria, but activity, like when you say activity, we're talking, I'm assuming, in a petri dish or
Yeah.
in a lab or something like that. So that's where the ivermectin for COVID kind of falls apart, because at the beginning, the initial evidence was just that, which I guess is maybe you can
Yeah.
enlighten us a little bit. But you start by just saying, okay, let's put a little ivermectin on the organism in it, outside of the body, or in some kind of controlled lab environment to see, does it do something? Is this worth pursuing? Right?
Yeah. No, absolutely. And that's where it started, with that drug repurposing thing we've just been talking about. When the pandemic was called, everybody was interested in working on COVID-19 as both, preventatives, vaccines, drugs. And so the repurposing machinery of various labs went into effect, right? And so one of the things that was in that list was ivermectin. So the first kind of hit the headlines was there was one paper which was not in a particularly prominent journal, showed that ivermectin had activity in vitro, as you're describing it, in a test tube essentially, against and reduced viral replication in tissue culture cells in a test tube. Now the drug concentrations that were in that test tube was something like 100-fold higher than you would ever safely give to a human, right, in terms of what's in the bloodstream. So that's the first point, right? So even taking away a test tube is not a human,
Mm-hmm.
and a virus in a culture disinfecting a cell is not, the natural pathogenesis and infection of a person. Even the drug concentration it took, if you use drug concentrations that you see in the body, in the bloodstream at a normal therapeutic level, it would have no effect on viral application. But it's you go up and up and up, and then it starts to have this effect, right?
Yeah.
So, and it's an interesting observation, and it's a totally legitimate experiment, and some of those things may lead to something, right? It's where it starts.
Mm-hmm.
But then, obviously, what happened then after that was a number of very small clinical trials were done, which, were underpowered and not well controlled, most of them. And actually, one of them was shown subsequently to be actually fraudulent, which was one of the big ones which hit the
Mm-hmm.
press and was subsequently retracted, some of them suggesting there was an effect both in as a therapeutic and some of them as a preventative, and some of them not. But the ones that showed an effect were small trials, not well controlled, and that's fairly typical early on in these things. People try stuff, and that's but the big trials had not been done to show was there anything in this at all. And so the press got a hold at that point, and then the story everybody knows is then the politicians got hold of it, the media got hold of it, and then people started taking it, right, based on no evidence
Mm-hmm.
of clinical effect. And I think just before we were
Mm-hmm.
talking, before we started the podcast, you mentioned this trial in Brazil, which has just come out, which is the biggest trial so far, looking at it as a therapeutic, where they gave, I think it was 3,000 people in the trial. They treated for 3 days symptomatic people and this was a proper double-blind controlled trial
Mm-hmm.
with a placebo group, and there was no difference in a 3-day treatment of the subsequent course of the disease in the treatment group and the control group. And so that's the biggest one yet, which shows no difference. And
Doesn't work.
so I mean, it's always very good to prove a negative, right? You could always argue, well, if you did slightly differently, it might have an effect. But the point is, there is no compelling evidence that has any clinical effect in a person at all yet. And so, that's where we are with it. And there are a couple of other big trials going on, which are not published yet. But, what you hear of them is, it's probably going to say the same thing. But
Well, I think it's important to so I wanted to go back to that thing. It's like it shows activity, and then you bring it to the next thing, you bring it to the next thing, to kind of show the chain, right? Like the steps involved as to how you would get from test tube to, okay, this works. And really, like as you explained, in an emergency with all the COVID-19, everyone rushing to do it, you of course are going to get these small, you don't want to call it anecdotal, but it's like it's not a true clinical trial, not a placebo trial. It's a doctor who's like, I've got all these patients, I want to help them, I'm going to try ivermectin and see if it works. And then he kind of says, well, it worked in these ones, and maybe it worked in these ones, or whatever. So you get this sort of signal, where one guy, and I mean, and this is a whole nother podcast, is the psychology of some of these doctors that are like staking their media reputations and stuff on ivermectin works, without having that clinical trial evidence. It's like, you're really sticking your neck out here, because people will do the clinical trials. And we will find the answer, and now we're finding that the answer is no. I think one of the quotes from one of the news pieces I saw about this latest trial was one of the doctors just saying, like, at some point we're going to have to stop trialing this because it's a waste of money.
Absolutely.
It's not working.
And that's exactly it, right? And then the media drives, like I say, proving a negative is difficult. So the whole hoopla actually drives the requirement to do research to disprove something, which there's no evidence that it's real, right? So how far do you keep trying to disprove something which everything says it's not real, but we need to try disproving it, right? So, and then for every one of these big trials, there'll be a little one comes out, somebody will pop up and say, oh, look, there's an effect. And so it all kicks off again. So it is, but I think it's forgivable in people who are not medically trained or not, necessarily scientifically trained. But when you see certain members of the medical profession taking the approach, that's the bit that is mind-blowing, right? Because, there's always this concept of regression to the mean. It's a term that's used, I don't know if you heard about it, but basically, if you're ill, 90% of things, 90% of the time, you're going to get better at some point, right? And so if you take a medication, a good proportion of people, you're going to get better, right? And the human bias of, I took that tablet and now I feel better, it must be doing something, is very strong. And so you often hear people say, well, listen to the people who've tried this, right? Listen, speak to them. It's all very well these scientists saying this. Speak to the people. I know this person who it worked for. But you could have taken a sugar pill and it would have worked perfectly the same, because you were going to get better anyway. And so the whole point of a proper clinical trial is to tease those things out. You would think most medically trained people would understand that. But it is surprising, actually, a proportion of the medical profession, the veterinary professions the same, still kind of take anecdotal experience of their own and weight it very heavily. And we're all tricked by that.
Yeah, this is like a, human psychology, right? Like this is a problem with human psychology. And I mean, this is the placebo effect too.
Yeah, absolutely. Exactly.
Which we've all heard of. I think everyone, knows the placebo effect at this point. So it's like, this is exactly what we're talking about.
Yeah.
It's this bias, this, I saw it, so it had to be true, or, I felt it, or whatever, or I'm a doctor and I witnessed all these people get better and stuff. But like you said, it's like, even COVID, not to minimize, is very serious problems. Very, lots of people have lost their lives, but most people that get it survive.
Exactly. Yeah.
And this was the problem with those trials. Like you said, there weren't proper controls and stuff. So it's like you're throwing the kitchen sink at these people. A lot of them were getting like dexamethasone and ivermectin and everything all at once. So it's like, you can't say, well, it was the ivermectin, or it was this, or it was the fact that we kept their room at a certain temperature, or we, like it could be any of these things, right?
Yeah.
Or they were just bound to get better anyway.
Yeah. Exactly. And I think all those things confound, and that's where we have clinical trials. And actually, that Brazilian one, there was no statistical significant difference between the two groups, the placebo and the treatment group. But the outcome, the trend, was to be worse than the ivermectin group, right? So it wasn't even the fact, you can argue with some of these trials that, if you look at the trend, well, if we did a bigger trial, we might then get the statistical power to show us an effect. So suppose the treatment group is just slightly better, but you do the stats and it's not significant. Well, you can do a bigger and bigger trial, and maybe it becomes. At which point you argue whether it's so marginal, who cares anyway, right? But in that Brazilian trial, it was even the other way around, right? The treatment group is slightly worse.
So I think we can really say that we can essentially put the nail in the coffin here for ivermectin and COVID. I don't see the ship turning around.
No. But people are still taking it, and I think the other argument people say, well, what's the harm? But I think the harm is, although it's a drug which is, we've said, widely used in the developing world, incredibly powerful drug. People have taken the horse and the cattle versions because they can get hold of them, and the dose of those things are, people are dosing at doses which are not safe. Not safe, and but even the human drug will occasionally have side effects and adverse effects. It's rare, but it happens. And then also people are taking them in a regime that it was never designed for, because when you use it against parasites, it's either a single dose or a 2 or 3 day course, whereas people taking them for months on end, which is an entirely different. So it's never been tested for these kind of things in terms of safety.
Right.
So we know if it's used properly, like it's supposed to be used for the organisms, it's supposed to be used in the regimes that have been tested, it's a very safe drug. If you start taking it dosage all over the place and periods of time it's not supposed to be taken for, we don't know what those effects are, right? So I think it's an amazing thing that people would take that risk personally, right? It's incredible.
But I mean, I don't know. We can start wrapping it up here, because I know you gotta get on with your actual important research instead of just being on the podcast here.
I'm enjoying this. It's good.
Yeah, but I mean, I think this speaks to and like you said, you can't fault people who, everyone's scared. It's COVID. It's a pandemic. People are scared. There's this bias against pharmaceutical companies for whatever reason, which again seems kind of silly. People will be like, well, they're keeping this from us. But it's like, none of that really makes sense in your conspiracy world, because the pharmaceutical companies still make money. Like, if you would think that they would want to be selling it to you and be like, hey, this works for COVID.
Yeah.
Like it.
Yeah, exactly. Well, Merck have come out, and Merck themselves have said, this has no effect for COVID. Do not take it, right? So it's ironic, isn't it, that the pharma gets accused of these things, but they're actually on the opposite side of this fence, right? So and it doesn't stop people taking it. So the same people who are probably saying, I'm not going to take the vaccine, which has been massively trialed to be safe and effective and all the rest of it. I'm not going to take that because I don't trust pharma. They're just trying to sell us a product. But they're taking a product which all the suggestions not suggestions, the proof, second proof says it doesn't do anything. And the pharmaceutical company saying, we don't want to sell it you. It's like, but they're still taking it.
Yeah.
So it's crazy, right? But it's hard, but it makes you realize how difficult it is to get scientific messages across. I mean, that's what you do for a living, right? And you're the expert on that, but it's just a really good example of it in terms of you can try pretty hard and the message doesn't get through, right?
So then I wondered, like, I'll get your thoughts on sort of this sort of broader science communication topic, because you just said I'm an expert, but hey, I'm figuring this out as I go.
Way more an expert than I am.
But I think it's important to get people like you who are working scientists perspective on this. Because, like, where do you see how do you, of course, we're just throwing ideas out here. I don't think either of us really know. If we did, we'd be doing it. But, like, where is the breakdown in knowledge? Is it that people don't understand clinical trials? Obviously, there's the psychology aspect that we touched on, where, I took this tablet and I feel better. Now there's fear, there's all this. It's like, where do you think you even start?
Yeah, I mean, it's very easy to go down a list, and we could talk for a long time on what the problems are, right? And how it doesn't work. How it works is much more challenging. How to get it to work. I personally think it really comes back down to scientific education from a very young age, right? I think that's the problem, because if people haven't had a science education and know how science works, then it's very difficult later in life to it sounds patronizing, but to explain it all, right? Because it's so far outside of their kind of world many people have got this vision of science that it's not how science is. And so unless more people, it's that thing of science should be compulsory from a young age at school for society's benefit, and not science just about in the way it's taught in schools. I think about this is how acid-base balance works, right? It's about how scientific. Because actually, if you think about it, nobody in schools, I wasn't, is taught how science works. What is the scientific discovery process? What is peer review? How does that work?
Well, even testing a hypothesis.
Yeah. So all those things in science, and I could be way out of date, but I suspect I'm not, that in schools, that isn't really, maybe it's improving, I don't know, but it never certainly was a big feature of it. And so people think of science as just a series of facts that are to be learnt and concepts to be understood, but they have no clue about the human story about how knowledge is generated. And I think if people understood that better, or more people understood that better, I think it would be easier to have these conversations, because everything we've discussed, it's the classic stuff. People go on social media or websites or whatever, and they just take the information that seems to make sense to them.
Or what they want to hear.
Exactly. Without really questioning where it came from. And then the flip side of that is if somebody is, shall we say, I'm trying to think of that word, but if somebody's doing it for nefarious reasons, it's easy to discredit science as well. On the other side of the coin is you can just make some random criticism of a study which has no weight, and people then don't know what to believe, right? So for example, the Brazilian study we just talked about, if you got a certain kind of person who's into conspiracy theories on the podcast with us, I am sure, and some of them are quite articulate, I am sure they'd make a pretty strong case as to why that study is wrong. And if you don't know what a double-blind clinical trial is and why it works, and what the motivations for the scientists doing it, and the peer review process and how that communicates inside, if you don't understand all that, why should you believe what I'm saying versus the other person on the podcast who's saying the opposite, right? So I think it's about understanding the process of science that we need more people to have, if you like.
Yeah.
I think.
Yeah,
but
like that.
That's
and
all
like,
that's all I've got.
Yeah. I mean, that it's like critical thinking, right? Like, so it's like there's the scientific method and critical thinking and this kind of thing. And I wonder if that doesn't then buffer people against the mistrust, right? Because that's the other thing that I think is getting exploited at the moment by these people that, they're doing it for money, obviously. Or, at the end of the day, when you follow these anti-vax or whatever rabbit holes, it's money. So it's like snake oil salesmen, or it's deeply religious people. Like those are the two, right? And they kind of go hand in hand. But I wonder if if you had that education you're talking about, or that knowledge, that understanding of you can kind of sift through the sort of the noise a little bit better. It doesn't buffer, against some of the mistrust, right? Because that's what a lot of people are selling, is mistrust in the institutions, mistrust in the pharmaceutical companies, this, that, the other. And everyone's always saying, do your research. But if you don't know what you're researching, and you can't know everything, you can't be an expert in all of these things, at some point you kind of have to just I'm going to trust my doctor. I'm going to trust, the research institutions or something like that. And if you knew the way that they're working, you might have a bit more trust in okay, they've done these trials. This is the standard. This is the framework. At the end of the day, you could always say, well, I don't believe that they actually did the trial. But then you're way far out there. But I think I tend to agree with you. And, when I talk to my brother, who's a school teacher, he kind of says the same thing. So maybe that's it. Yeah.
And I think it is. You make a good point about the trust, because it's exactly that. That's where the lack of trust comes from. Who do you trust, right? And I think if you understood how science works in terms of professional science and all that stuff, I think it's easier to trust certain sources than others, right? And for example, you hear conspiracy theories about that scientists is being paid to do that, right? I even saw, some person like this being interviewed, and it was a politician, a Republican politician, I can't remember who she was, but she was basically talking about evolution. It was, she's an anti-evolution person, and she was basically saying, well, of course, you do know that Darwin was paid to produce this theory.
Oh, I saw this.
Right? Yeah. Right? And it's like, for anybody who understands how science works, you know that is not true. But if you don't understand it, then you might go, well, I didn't know that. That's interesting. So
Yeah, sounds nefarious.
That's just an example. So you don't know who to trust. And I think, as a scientist myself in my own field, you can't read absolutely everything that's published on everything and understand it all at every level, right? But there's a system in place where part of the skill of it is knowing what to trust and why, right? And that's the piece that as a scientist you kind of spend your life doing it. And so it's difficult then if people don't have that background, to know where to start with the conversation, right? Because you assume a lot of stuff and then people, it's easily derailed if people don't have that trust in certain systems. The other thing I think which doesn't help is the way the media approach it in a number of ways, right? On the one hand, you've got the sensationalist thing. It's always getting the headline, and so that doesn't help. So somehow that's got to stop. About how, I don't know. And then the other thing is this argument of false balance as well, which, is this thing where... And the BBC, actually, although they're very good in many ways, and very good compared to many... still have gone down this track of always wanting to provide balance.
Right.
So if there's an argument, we must get a spokesperson on either side of this debate.
No matter how ridiculous the other side is.
Yes, yeah. So it's like, if you were talking to somebody about satellite navigation, it's almost like saying, well, we need a flat earther on here to point out not everybody believes the earth is round and these satellites might be all nonsense, right? And we're going to give them each 10 minutes, right? So you wouldn't do it. But in medical matters, quite often there is. And the anti-vaccine lobby, they're given way too much airtime. And it's this false balance because you only should be providing balance where there is something to debate, right? And so that's another side of it, which and again, what the mechanisms are for trying to rectify that is, beyond my understanding of how media works. But yeah.
Yeah. I don't know what the answers are. Media training, critical thinking skills, all of these things. But I think, I don't know, I do hear more about this, becoming part of curriculum, or people are at least talking about it becoming part of curriculum, because we haven't even touched on the social media angle of all this, which takes all of these problems that we're talking about and then just, amplifies them to the max. So the people growing up today are how are they ever going to know what's true and what's not in the next 20 years, It's a weird thought.
It is. And I think the other thing, the final thing on, thinking about problems is these problems that scientists have, I think, and this podcast might be an example of it. We tend to go into a lot of detail, right? So if you let somebody like me talk, actually start going, it's just because, it's, and I think that turns people off as well. So if you overdo it, and I think also we've got to learn to be more disciplined about that. Mm-hmm. But the challenge is, of course, science is messy, it's complex, and it's not always clear cut. And as a scientist, you tend to go into that. And we're comfortable with dealing with uncertainty in our profession, if you want to put it that way. Whereas people on the other side of the fence quite often massively oversimplify, give clear messages, which are easy to understand. And so when these debates happen, sometimes you've got somebody on the one side, the scientist, who just sounds like it's confusing, it's difficult, they don't really know. Mm-hmm. You've just said they don't really know. And then somebody on the other side saying, no, it's very straightforward, this is the answer. Mm-hmm. And that's another challenge. And as a scientist, I kind of don't know how to handle that, to be honest with you, because if you start oversimplifying your own message, then that's not right either. Right? So it's a really difficult thing to tackle. And I know that, there's a lot of people over the years. The evolution debate and the religion debate is an interesting example of it, because there are people on the evolution side who will refuse to publicly debate with the anti-evolutionists, partly for those reasons, because it's very easy to give the negative, distorted, simple message. Mm-hmm. And sometimes the debate gets derailed because people on the other side are trying to explain this complexity and subtlety.
But I think this is where
it's hard, right?
what you were saying, like the education about how science works, because this was one of the things that really always, drew me to science, and what I really enjoyed about, working in the lab and stuff and just talking with everyone else is how, like you said, people are comfortable with uncertainty. There's always something you don't know, there's always the next question. And you're really at the, I've said this a million times on this podcast, people who listen regularly, and I'm sure there's 5 of them, probably get upset with me because I say it again, but it's like you're on the tip of the spear of the knowledge, like of knowledge creation. And that's the amazing and the exciting thing. And I think if people understood more that this is what science is, and then this is like, what scientists are, enjoy about it, and they'll be very open to tell you, what you know and what you don't know. I think during the discussion just now, I think you've said it several times, well, we don't really know how ivermectin's doing this or how it's doing that. And it's like, but that's a good thing. But like you said, it's taken in another format, in another field, it becomes a very bad thing.
I mean, a really good example of that, actually, and we probably should finish because nobody will listen this long, but I think so. But one of a really good example of that was the COVID situation, and the advice the CDC and people at Anthony Fauci had given originally. So obviously, when COVID started, by definition, it was a new virus. We had limited understanding of it. And so if you remember back to the early messages, it was a lot of the control of transmission was around washing hands, decontaminating. And actually, they openly said early on they didn't think the masks were that important, right? And that was based on limited data, which was pointed out at the time. But then as the studies were done and the evidence gone, it becomes the biggest single way to control it other than vaccination is by double masking, right? And then that became the message. But a lot of those conspiracy people, anti-mask people, all that stuff, use this against the scientists saying, you're just flip-flopping. You see it on, the Fox News journals, flip-flopping all the time, says one thing, next minute. But the reason it's not flip-flopping, it's changing your opinion based on evidence as you acquire it. And that's a good thing. It's a good thing to change your mind. It's a bad thing not to change your mind. But then that's where it's the example of this complexity versus simplicity. If somebody's just shouting the same thing over and over again, it sounds like they're pretty convinced, right? And they're convincing to some people. But it's not good, and so that debate still happens. It keeps getting brought up. We've changed your mind so many times. Why should we listen to you? We change it. Whatever mind changing is going on is based on updating our evidence, and now iteratively improving the advice. So, but it's hard to get that across sometimes, right?
Well, do you think that maybe that's the thing that's lacking, is being upfront about that, what we know and what we don't know? Because I think and again, people that have listened to this podcast have heard me say a version of this many times, but I kind of feel like, I understand it from the public health officials and the politicians and people, that there's this new emerging crisis. There's all, everyone's scared and we want to keep people safe and stuff like that. But to go with these sort of absolute statements like, got to do this, got to do that, rather than be like, look at everyone, we don't know. Just, you got to trust me. We don't know. It's going to change. Being inside is worse than being outside. So, wear a mask inside, but you don't necessarily have to do it outside. But then it became this like, you got to wear a mask. And you saw people wearing masks outside, or, they're closing playgrounds and stuff. And it's like, at that point, we kind of know that that's not really the danger, but I think there was a reluctance to acknowledge the nuance and acknowledge the gray area and acknowledge what they don't know, for fear of whatever bad thing's going to happen. It's better if we just do it this way, talk down and just tell people this is it. And I don't think that was necessarily the motivation, but maybe that's just the way it unfolded. But I wonder, if that's kind of, and maybe you buffer that with education earlier on, right? Like if we maybe in 20 years, if something like this happens again, we'll all have this memory and be like, well, let's figure it out first. It's going to change like it did last time. I don't know. Yeah.
No, I agree entirely with you. I think that is the right approach. And you're right. It happens with a lot of public health advice that, the thinking has been you need to keep it simple to keep the measures simple, which, there is some truth in that, obviously. But you've got to be careful you don't overdo it because of exactly what you said. You oversimplify and then you back yourself into a corner when you have to kind of, change something and the rest of it. So I think absolutely, I think uncertainty and getting that across and being honest about it is way better. That having been said, you've got to be aware though it will be used against you because of the examples I've given. Some people will then use the argument that they don't know what you're talking about because you keep, don't sound like right? So I think, but again, it's not going to happen overnight. But I think if the culture could evolve to that, and as you say, including earlier education, I think that's probably the biggest thing that would change it. But it's not going to happen in a year or two, right? It's a generation probably.
And there's a lot of, confound, like you said, social media, there's all these confounding issues. I personally think that people should be less worried about what the opponents
No, absolutely,
be honest, be genuine, because that's what people respond to, right? So if you're a good speaker, you're a good communicator, embrace the unknown. Because if you look at like a lot of the popular science communication stuff, a lot of it's space because people are just really into space. But, Carl Sagan's and the Brian Greens and like all these guys, right? It's always about the unknown. It's always about the mystery. It's always about so people like it. People do like it. Maybe not so much when it's about their health.
It's a mystery. I don't know why you're dying. It's a mystery. Yeah, but yeah, it's no, it's a good point. Absolutely. And I think the thing is, and it's an interesting one. I think it's more to do with education than, for example, intelligence, right? I mean, because you can have the brightest person in the world, and if you haven't been exposed to that stuff, particularly earlier in life, it's not about a lack of intelligence. It's just about a lack of way of thinking,
a training,
which has come about over a lifetime. Yeah, training. So I think, it, and vice versa, right? I mean, I don't think, in a way, this isn't rocket science, right? I mean, this is the baffling thing about, if you think about the logic of a double-blind clinical trial, going back to that, it's not rocket science that you look at a lot of people. You don't have any biases, and you look at the data, and that's going to tell you better than asking the guy down the street whether he feels better or not, right? It's that should not be. You shouldn't need to be a brilliant mind to.
It's not
get
controversial.
That. You don't need to be, right? No, but there are many intelligent people who don't get that. So it's nothing to do with intelligence. It's to do with education and where you've come from and what you're exposed to, I guess.
Well, John, this has been great. I've enjoyed it. I know my 5 listeners will enjoy it as well. So,
well, I'm aware you should work hard on interrupting me when I'm beginning to prattle on, because I'm aware sometimes I go on a bit too long on some of the segments.
No, I think it's great. I think you're a good storyteller. I think you got a knack for some of this stuff. So if you ever want to start your own podcast, I'll help you out with it. But for now, you're welcome to join me anytime on this, and I really appreciate you taking the time.
No, I really enjoyed it, and you're a good host, so I'm impressed. Thanks for inviting me.
And there we have it, the true history of ivermectin. Thank you so much again to my guest, John Gilleard, for joining the show, and for you for sticking around to the end, and for rating and subscribing the podcast like I know you will do. Please, please, please rate, subscribe, follow wherever you get your podcasts. Head over to the website, twobradforyou.wordpress.com. Find out all of the different ways you can get in touch with the show. We want to hear from you. Hit us up on Twitter or Instagram at twobradforyou. And that's it. Enjoy the rest of your day. Thank you so much for listening, and we'll see you next time. Bye for now.